So let's define a few terms. So let's define what we mean first by an observer. A single observer is someone who occupies a particular position in space at any instant of time in their coordinate system. Okay. Now let's define a frame. So a frame refers to a collection of hypothetical observers who are spatially separated at rest with respect to each other and have fixed distances between each other and have synchronized clocks. So the way to picture this is if you take Om Prakash and his friends and you imagine an infinitely dense collection of friends, and all of these friends have synchronized clocks, then and they're all at rest with respect to each other. They're standing on the platform, so the distance between any two of them is not changing with time. Then these coordinates that are defined by this collection of hypothetical observers is called a frame. Okay, and any hypothetical observer at some position, for example, an observer here, C, would be able to tell other observers in this frame when a particular event occurred. And since the coordinates of observer C with respect to some well-defined origin are fixed in this frame, every observer will know where the event occurred. It occurred at observer C's location, and they will all know when it occurred because they all have synchronized clocks, and they will all agree on the time at which that event occurred. And finally, we'll define the concept of an event is something that occurs at a particular observer's location, so a particular point in space, at a specific instant of time. Right? So for example, a lightning strike hitting observer C at time t is equal to 10 seconds as measured on all these synchronized clocks, that is a particular event. Okay, so this is also called a space-time event because it has a specific location in space and a specific location in time. So now, in light of these definitions, we can go back to talk about the implications of Einstein's postulates. So when we say that simultaneity of events at a distance is relative, that means that two events which are perceived to be at the same time instant as seen by one observer are not simultaneous events as seen by a second moving observer. The second postulate, the second implication, which is that lengths are relative, is that the simultaneous events of locating the endpoints of a rod are not simultaneous according to a moving observer, and therefore the moving observer will perceive a different length for a rod than an observer who is at rest with respect to that rod. And finally, time intervals are relative. So if you take a clock located with a particular observer, and you take a clock which is moving along with another observer at a constant velocity with respect to the first, those clocks will appear to tick at different rates. So now let's try to formally derive the dictionary of special relativity transformations between two observers who are moving with respect to each other, or two frames rather, that are moving with respect to each other at a constant velocity v. And let's take one frame, we'll call it S, and another frame which we'll call S prime. S prime. Okay, and what we mean when we say we want to derive the special relativity transformation is that in frame S, the coordinates of any space-time event are given by a spatial location in three spatial dimensions, x, y, z, and a time instant t. In a frame S prime, that same event is located by a coordinate system where the coordinates are expressed as x prime, y prime, z prime, and a time t prime. And when we say we want to find a dictionary or the transformations of special relativity, what we are looking for is how can we express x prime as a function of x, y, z, and t, and similarly y prime as a function of x, y, z, and t, z prime as a function of x, y, z, and t, and t prime as a function of x, y, z, and t. Okay, so if we knew all these functions, then we know the dictionary, or we know the special relativity transformations. And these transformations should depend on the parameter v, which tells us the velocity of frame S prime relative to the frame S. So all of these transformations in the dictionary depend on what this parameter v is. Now, one thing that we can do is choose our origins in each frame. That is, we can choose an origin in space and an origin in time. And we can choose them in such a way that when x is 0, y is 0, z is 0, and t is 0, we want x prime to be 0, y prime to be 0, z prime is 0, and t prime is 0. We always have the freedom to choose at least one space-time event, the coordinates of one space-time event as seen by one observer, to agree with the coordinates of that same space-time event as described by a second observer. Okay, so we will make this choice that the dictionary equivalent of the points x is 0, y is 0, z is 0, and t is 0 is the same as x prime is 0, y prime is 0, z prime is 0, and t prime is 0. Now also, by the principle of isotropy, that is rotational symmetry, we can also choose an orientation of our axis such that the x prime axis coincides with the x-axis, the y prime axis coincides with the y-axis direction, and similarly the z prime axis coincides with the z-axis direction. Okay, so this uses isotropy. And finally, we will use the principle of homogeneity to argue that the transformation must be linear, which means that there should be a matrix such that if I write t prime, x prime, y prime, z prime as a column vector, there is some 4 by 4 matrix which multiplied by the column vector of t, x, y, and z, okay, will relate the new coordinates t prime, x prime, y prime, and z prime to the old coordinates. Okay, so these are the old coordinates of a particular space-time event. These are the new coordinates. Okay, and this matrix should only depend on V, but it should not depend on t, x, y, and z, or t prime, x prime, y prime, and z prime. Okay, so this is what we call a linear transformation. And we'll call this matrix lambda, where lambda is a function of V. Okay, now you can ask, why does homogeneity imply this? Well, homogeneity just tells you that there is no preferred origin in space. Now you could ask, why does the principle of homogeneity imply that the transformations are linear? Let's take a specific example. Suppose the transformation was nonlinear. Suppose, for example, x prime was proportional to x squared, where a is some constant. Okay, then what that would imply is if I take 2 points in frame S, which are at locations x1 and x2, the length of these, the length of any object which stretches between x1 and x2 would be x2 minus x1. If I take the same object and put it at a different spatial location, that is at location x1 plus c and x2 plus c, its length would still be x2 minus x1. But now let's ask, what would the observer S prime see? Well, if we use our dictionary, S prime would see that the first end of this rod, by using the dictionary, is at location x1 prime, which is a x1 square. And the second location of the rod is at x2 prime, which is at a x2 square. And so what they would measure for the length of the rod would be x1 prime minus x2 prime, which would be a times x1 square minus x2 prime square. Minus x2 square. However, if I had moved the rod, then according to the first observer, it's now at x1 plus c and x2 plus c, but its length is still the same. The length has not changed. But according to observer S prime, if I take that same rod and I moved it, its length would now, or its coordinates would now firstly be a times x1 plus c square and a times x2 plus c square. And its length would be something like this. It would be a into x1 plus c square minus a into x2 plus c square. And this new length would depend on c, okay, where c is this constant amount of displacement that I've made of the rod. So the length of the rod would depend on where it's located in space, and this obviously violates our principle of homogeneity. There's no preferred point in space where the rod is longer or shorter. It should just measure the same no matter where it's located. Okay. Each observer might measure a different length for the rod, but the length that they measure for the rod should not depend on where the rod is located. So observer S prime would measure different lengths for the rod at different locations, and that's why this nonlinear transformation would go against the principle of spatial homogeneity. Now let's suppose, without loss of generality, that the frame S prime is moving to the right as seen by frame S with a velocity or a speed v along the x-axis, as seen in frame S. Okay, now since only the x-axis is picked out as a preferred direction, nothing should change in the y and z directions, okay, by the principle of isotropy. So therefore, if we look at our transformation matrix, this tells us that the only non-trivial part of the transformation should involve time and the x-coordinate. So that is, this 2 by 2 block over here is the only thing that's going to be non-trivial. Y prime will just be y, so this entry will be 1, z prime will be z, everything else will be 0. Okay, that is, the y prime and z prime directions do not mix with each other. Y prime would just be y, z prime would be z. Okay, now let's consider an origin O in frame S. This is the x-axis. And let's consider the origin O prime of frame S prime with coordinate x prime. Now, the location of origin O prime with respect to O is moving in such a way that it covers a distance x is equal to vt. This is the coordinate of the origin of the S prime frame as measured in frame S. Okay, so what that means is that when x prime is 0, we should have that x is equal to v times t. Okay, so what that tells us is if we write down this 2 by 2 matrix, so let's call this 2 by 2 matrix, we'll call it small lambda, and we'll denote the entries now of this matrix in such a way. We'll write this as t prime is lambda 1 1 t plus lambda 1 2 x, and x prime is lambda 1 or lambda 2 1 t plus lambda 2 2 x. And now what should happen is when x prime is 0, we also have x is equal to vt. Okay, so that tells us, if plugging in when x prime is 0, x is equal to vt, if we plug this into this second equation over here, what that gives us is 0 is equal to lambda 2 1 plus lambda 2 2 into v whole thing times t. And this should be true for any instant of time. So that tells us lambda 2 1 plus lambda 2 2 times v is 0. Okay, this is our first equation. Now let's consider a light beam that is sent out from the origin, so from 0 0, and this is t is equal to 0, x is equal to 0, as seen by the first observer, and t prime is 0 and x prime is 0 as seen by the second observer, since we've chosen the space-time point to coincide in coordinates as seen by both observers. And let's imagine that you send out a light beam along the x direction with a speed c. Okay, and now this light beam would satisfy this equation, that is x square is c square t square. This would be true whether you send it out in the positive x direction or the negative x direction. So we'll write this equation more generally. And in the primed coordinate system, this equation would be x prime square is c square t prime square. All right. And now we can use our dictionary to rewrite x prime and t prime in terms of x and t. So the second equation, so if we call this A and B, this is describing the same light beams but in different coordinate systems. We can rewrite our second equation using our dictionary over here. So let's just copy that. So using our dictionary, we can now write the second equation as lambda 21 t plus lambda 22 x square is equal to c square times lambda 11 t plus lambda 12 x square. And now we can rearrange this equation to collect all the terms with t, with t square, x square, and the cross terms with x and t. So we'll write it like this. We'll put all the terms with x square on one side. So that would be lambda 22 square minus c square lambda 12 square times x square is equal to, and we'll put the terms with t square on the right hand side, so c square lambda 11 t square, lambda 11 square minus lambda 21 square times t square. And finally we'll write the cross terms plus c square times 2 lambda 12 times lambda 11 minus 2 lambda 21 lambda 22 times xt. Now this equation, which is just b rewritten back in terms of the old coordinates, should be exactly the same as the original equation x square is c square t square. So what that means is we can equate the coefficients of x square on both sides. So the coefficient of x square here is this, and the coefficient of x square here is 1, and I've just equated them over here. Similarly, we can equate the coefficients of t square and the coefficients of x times t, which is 0. So c square lambda 12 lambda 11 minus 2 lambda 21 lambda 22 is equal to 0. And we now have 3 more equations for our coefficients combined with our fourth equation, which we had up here, lambda 21 plus lambda 22v is 0. So now we have 4 equations for these 4 unknown coefficients, lambda 11, lambda 12, lambda 21, and lambda 22. So this is a homework exercise for you, is to solve these equations and to show that we get the following things. We get lambda 11 is equal to 1 over square root of 1 minus v squared by c squared. Lambda 12 is v over c squared over square root of 1 minus v squared by c squared, with a minus sign here. And lambda 2, 1 is 1 over square root of 1 minus v squared by c squared. Lambda 2, 2 is minus v over square root of 1 minus v squared by c squared. So this finally gives us our transformation between observers s and s prime. So t prime is related to x and t using this equation. And x prime is related to x and t using this equation. So finally, we have the dictionary for special relativity, and we complete this with the equations for y prime and z prime. So this gives us our dictionary for special relativity, or the special relativity transformations. We'll discuss the implications of these transformations in the next class.